Manchester, and he will speak about some effective special point results.
Thanks very much. So thank you for inviting me. I'm afraid my talk will be in English. So I'm going to talk about some effective special point results. So to begin with, the special points, like I'll be talking about Manin-Mumford, so I was just going to start by introducing Manin-Mumford. So suppose E is an elliptic curve. Say over Q bar. Then the complex points of E is analytically isomorphic to C mod a lattice. So for a lattice, so we can see that there are lots of torsion points on E. So they have torsion points of all orders. And Manin-Mumford is about the distribution of torsion points on subvarieties of abelian varieties. So let's take a product of elliptic curves, or an abelian variety. More generally, so the Manin-Mumford conjecture, which is a theorem of Raynaud, describes the distribution of torsion points A, so I'll write A tors for the torsion points of A on varieties living in A. So what sort of things might have lots of torsion points? So e.g. if I took A to be E squared, and I took V to be E times 0, then there's lots of torsion points on V. Or you could take, V could be E times the torsion point. Or more generally, V could be a translate of an abelian subvariety by a torsion point. So I'll call these torsion cosets. And Manin-Mumford kind of says that these things explain the torsion on V. So maybe I'll state it over here. Yeah, so this is the theorem. So if I'm not pressing hard enough with the chalk, please let me know. I'm trying. So suppose A is an abelian variety. V a subvariety say all defined over cube R. So everything today will be in the number field case. So then there are abelian subvarieties, B1 up to Bn and torsion points B1 up to Pn such that if I take the torsion points lying on V and I take their Zariski closure, this is the union of these torsion cosets. So this describes the torsion lying on V. In particular, if our V doesn't contain any positive dimensional torsion coset, then it will contain only finitely many torsion points. Finitely many torsion points. On V. So I'm interested in effectivity. So there's a question, if you're given V and A, say it doesn't contain any positive dimensional torsion cosets, could you find these finitely many torsion points?
Find them or find the number?
So I will say something now. So can we find these points? So Hrushevsky 2001. Well, so a special case gives an upper bound on the number of torsion points, say in this situation. I mean, this is really a special case. It describes the general situation. That's enough. In these kind of problems, if you can bound the number, you can find them. So this is quite different to like Mordell kind of problems. So I'll say more about that in a second. So this suffices to find all points. So for instance, using a result by Massa. Which I'll mention in a minute. I'll state the result by Massa in a second, because we need it in a different context.
Actually, the method was using difference equations.
Yes.
And if you prove something by that method, so the set of points is contained in another finite set, which is defined by difference equations,
Is there a different way to compute? Or?
So I don't think you need mass or anything like that. I mean,
You can actually sort of write down equations.
you write down equations which also have function A solutions, maybe more, but then you can just check among these which ones are torsion.
Yeah, so that's a different way you can do it. Rather than using, once you've got the point, once you've got the number of points, if you've got equations describing them, you can kind of compute them all and just check if they're torsion. Yeah, well, then those two ways will occur later.
Sorry?
The two different ways, there's a proof later where we have two different ways to sort of conclude. But, okay, so I don't know the details of your proof. So.
No, what I'm saying is you don't need to know
Yeah.
details. The moment you know it's done by difference equations,
Okay.
it has to be, that it's done by finding a bigger finite difference equation, then it's automatically effective.
So next I was going to sketch, so in 2008, Peter and Zanier gave a different proof. Of Manin-Mumford. And I'll sketch their argument, because it's the kind of argument we'll use later. So let's say take V a curve in the product of two elliptic curves. Not a torsion coset. And say everything defined over a number field K, and then let's let pi be the exponential map given by p functions. Let's let omega I be a lattice for EI, and we can write down a set which kind of moves the torsion points to rational points. So let's let X be B1 to B4 in 0, 1 to the 4, such that when I take the exponential of the point corresponding to these b's, so that's this, this lies in V, then torsion points on V correspond to rational points on X. And if we have a bound on the order, we get a bound on the height of the corresponding rational point. So if P in V of C has order n, then the corresponding point, we get a point, a rational point, on X of height at most n. Now this X is definable in Rn, in the O-minimal structure Rn, because I'm only using kind of bounded pieces of the exponential. So we can use the Peeler-Wilkie theorem to count points on to count rational points on the transcendental part of X. So it gives the bound of the form if I look at the rational points on the transcendental part of X of height at most n, then this is bounded by, the number of these is bounded by C epsilon n to the epsilon for any epsilon. So here the transcendental part is X with the algebraic part removed, and the algebraic part is the union of all the connected infinite semi-algebraic subsets of X. So the union of Y contained in X such that Y is connected infinite and semi-algebraic. But in our case, because of this assumption that V is not a torsion coset, a theorem of Ax implies that X is its own transcendental part. So this is where we use the assumption on V. So in this case, Peeler-Wilkie says oops, wrong again. Now, if we have a point P of order n, then any conjugate of P where we fix K will also have a point, will also be a point of order n, and this is where the result of matter comes in. So Massa showed that P has large degree in terms of the order. So for some positive delta, so now I can take conjugates and I get more and more rational points. So now we have, this gives us a lower bound for this. So and then if I take epsilon small enough, this bounds the order around. This bounds the order. So
This C and delta, these C and delta were effective in Massa?
so I'll say some.
Because I remember there was also an argument with Andre, and it was not effective just because something it was quoting was not at that time.
Okay, so this is effective. Delta's explicit. I just can't remember it.
And also for Boolean variety?
Yes. And the C is effective, and that may even have been worked out. So this bounds n. So once you bound n, you have finiteness because there's only finitely many points of order n. Yeah, so this is proved using transcendence techniques, and you get effectivity. Okay. So that's the P-Lasagna method. I'm not going to do it again later. I'm just going to say how we modify it. And it's been used in many other settings. Okay, so we can also ask about uniformity. So what happens if I kind of vary the elliptic curves? So building on work of Dimitrov, Gao and Habiger, Gao, Gay and Kuhner proved the uniform Mordell Lang. So I'm only going to state their result in the Manin-Mumford setting. They prove much more. So theorem. This is from 2021. So if you're given a G and a D, so this will be the dimension of the abelian variety, this will be the degree of the subvariety. There exists a C such that V is in an abelian variety of dimension G, and V has degree D. And over Q bar, or C, over Q bar. then the torsion lies in a union of at most C torsion cosets. So this C doesn't depend on A at all, just on its dimension. So in particular, if V happens to have no positive dimensional torsion coset in it, you get a bound on the number of torsion points, which doesn't depend on A. So we prove a different kind of uniform Manin-Mumford, which is way less good in the sense that it applies to far less A, but it has a different kind of character at the conclusion. And it has other applications.
So A is not fixed, yeah? So
yeah.
what about the embedding?
So yeah, you take a sort of uniform choice of embedding, or you can have a line bundle.
So it's for a given family. It's for a given algebraic family of given varieties.
No, their result you.
No, it's not. Okay. But then
No.
what is the degree? I mean,
Pardon?
what is the degree?
Yeah, so I think you fix an A and a line bundle, and then the degree is with respect to the line bundle.
So it's a principally polarized family or not?
I can't remember.
Yeah.
But you can probably assume it's principally polarized by like going to a fourth power or something. Isn't there some trick like that?
Yeah.
Science trick. Yeah.
And that's not going to really.
Right.
Sorry.
Well,
I don't see how you explain the finiteness by just knowing that it lies inside torsion cosets.
Okay, so their result's a bit more precise. Yeah. The torsion cosets are contained in V, so I should say. Otherwise, it's trivial. I just take A to be my torsion coset.
do they do that for the Bogomolov version as well?
So for Bogomolov,
Yeah.
I believe someone, I think maybe Lars did that earlier. So what they do is Mordell-Lang. I mean, they have a group. And,
So where is the finitely generated group introduced? I mean, this is not Mordell-Lang, this is torsion. You wrote.
yeah, I've only stated their result in the Manin-Mumford case.
Yeah, but if it's Mordell-Lang, it does not include the torsion case.
Yeah, it's like
So it depends. Yeah, I see.
it's
So
finite
by
rank.
definition, you go to the, there's also a version just for finitely generated.
Yeah. No, this is the like I don't know Fulting's version or. But I'm not going to talk about it. But it's a much better uniform result in many ways than the one I will state. But as is better in some ways. Okay, so I need a definition. So an elliptic curve has complex multiplication. This is over cube R. Endomorphism, if its endomorphism ring strictly contains Z. So if it has other endomorphisms beside integers. So this is rare, but does happen infinitely often. Okay, so here's our theorem. So this is joint work with Gareth, Binyamini, Schmidt, Margaret Thomas. So fix G an integer, and epsilon greater than 0. And there are effective C and M with the following property. So suppose A is a product of G CM elliptic curves. And I need, given my equations over a kind of minimal field of definition, so I want just the field where I join the J invariants of these E's, so I can always do that. Suppose V in A is defined over a number field L extending K. Yeah, since these have CM, these will be algebraic numbers here. So let's suppose V does not contain a positive dimensional torsion coset. Then if P on V has order n, we have n is bounded by C L over K to the 1 plus epsilon times the degree of V to the M. So, okay. So we have our product. So now our abelian variety has to be a product of CM elliptic curves, so it's very special. And we take a variety in it defined over an extension of the base field. Then and suppose it doesn't contain any torsion cosets, then we get this bound on the order of a torsion point.
So K is Q adjoint.
K is Q. Yeah, sorry. K. So I need this because otherwise this isn't really doing anything. I mean, I could just sort of take K to be bigger and then I'd be losing this. Okay, so let me make some remarks about this. So it's less uniform than this because we have this assumption that it has to be a product of CM elliptic curves. But we bound the order and it's effective. So I don't know about effectivity here. And if it was effective, then I think at the point where you use the bound on the number to bound the order, you'd introduce dependence on the A. So we avoid that here. So there's related work by Gabriel Dill In particular, his result implies the case where A is a power of a CM curve. Maybe with different exponent. I think he has a larger exponent here. His methods are a bit different though. Yeah, we can remove star. So we then get a bound on the degrees of the subgroups and so on and the number. It's just more convenient to give a talk with the assumption. But later, in the results I'll state later, we can't yet remove the corresponding assumption. So these things, the bound has to depend on these. So if you're bounding the order of the order of the points, you need the dependence on the field of definition because you can just put a point of big order on your variety. So it's a bit different to the when you bound the number of points. And this kind of particular kind of dependence you can't get in general. If you let A just be a power of elliptic curves, but remove the CM assumption, then this is not true anymore. Probably the right thing is a Q here, but I think we don't know how to prove that. I think you need some quite strong conjectures to prove that. But pardon? So here, so what I'm saying is that this particular bit of the bound, the L over K, isn't true if you just take A to be a power of an elliptic curve without the CM assumption. I think there are other cases where it is true. You need some assumption on the E. And I think the right conjecture is that you have, instead of L over K, you'd have L over Q in general. Q, the rationals. So this is really about CM things, and it's really about special things, because it uses some things about Schmidt varieties in the proof.
And is one perception on the correct?
I don't know. I think probably one is the correct exponent. I'm not sure though. And this N will be awful. Yeah. And the C. Yeah. I think this kind of effectivity is like it's an in-principle effectivity. It's interesting theoretically. It's not. If you actually wanted to compute torsion points in special cases, you'd probably do something very different. Okay, so I'll say a little bit about the proof. So we use the Pilatanier method. But we can't use the original Peeler-Wilkie theorem because it's not effective. So we proved an effective version of Peeler-Wilkie.
Can I ask one more small question? So the point there lies in in the C points on V.
Oh, it could be a Q bar. They all lie in Q bar.
You're not obliged to take the L points there.
No, this is counting, like if you took the L points, you'd only have, you'd have a bound on the order already.
Okay.
So the Manin-Mumford is really about the points in the algebraic closure, the torsion points in the algebraic closure. Because as the n gets bigger, the degree goes up. So, okay, so so in place of Peeler-Wilkie, we use an effective version. For Pfaffian functions. Which we prove. So now we could also use sharp minimality. But it doesn't make any difference, really. It doesn't improve the results. We end up with the same result.
So this effective version is for restricted Pfaffian functions?
So we have effective versions for either. The effective version, we use the effective version for restricted Pfaffian functions because that's how we get this. So for restricted Pfaffian functions, the constant in Peeler-Wilkie is polynomial in the degree of the Pfaffian functions, and that in the applications corresponds to the degree of the variety. In the unrestricted case,
It's just effective.
our proof is just effective. Yeah. I mean, presumably, unrestricted Pfaffian functions are sharply amenable, but we don't know how to prove that. So if you had sharp ominimality, you would get the polynomial dependence on the degree. But yeah, for us, restricted is enough. It also works if you have unrestricted with an existential definition. If you're actually handed the existential definition, like as part of the data. Okay, so we have to know that this applies. So for that we use some earlier work by me and Harry Schmidt. So this gives a uniform definition of Weierstrass P functions in terms of Pfaffian functions. So we give uniform definition, uniform Pfaffian definition. Of P functions. So this is a bit technical. I'm not going to go into it. So 1 and 2 together, they make like the Peeler-Wilkie part of the Peeler-Zanier strategy completely uniform as long as you're working with a power of elliptic curves. So there's no CM yet. And the thing that's stopping us doing this in the abelian case is this step. So we haven't done it yet. So we know that there are uniform Pfaffian definitions, but we don't know how to bound the complexity of them in the abelian case. So the existence of them follows from ominimality from the results of Kobe and Sega.
So in this sketch, have you explained yet why CM, how CM comes in?
Pardon?
Have you explained yet how CM?
No. I will now do that. But I mean, it has to come in the Galois bound, right? Because I've just said that. So 3. The Galois bounds due to Gal. This is where CM comes in. So I can state as a result. So this applies to CM abelian varieties generally. So suppose I have a G and a theta. And there's an effective C greater than 0. Such that if A is CM abelian of dimension G, with minimal field of definition K, and P has order n, then the degree of P over the field of definition of A is large uniformly. So this is from Gauss' proof of Andre-Oort for mixed Shimura varieties. So these CM elliptic curves and CM abelian varieties are mixed Shimura varieties, and that's where this is used.
And can you remind us what is CM abelian? Then the morphism range.
It's contains commutative algebra of large dimension.
Contains, or is just it has it as infinite index or something? More or less, maybe it is commutative.
I can't remember, but I don't need it because I'm only working with these.
And then it means that each one is CM.
Yeah, exactly. But Gauss' result is general. It's not.
Sorry?
Gauss' result is general in the abelian case. It's not to do with elliptic curves.
Oh, if you wrote CM.
Sorry, general like CM abelian,
Yeah.
rather than
According to Wikipedia, it should contain the commutative subring of dimension 2G.
large.
Of course. Yeah, thank you, sorry.
Sorry.
Yeah. No, of course, yeah, I got mixed up.
I mean, I'm not really the right person to ask about general abelian things.
Yeah, it should contain, sure.
Yeah, so here the CM isn't used. And these, if you had...
Is it possible to say a word about his method for doing this?
I can't, no. But it's to do with class field theory. So there are more explicit results. If you just have an E, fixed ECM, and you can get this kind of uniform result kind of from classical class field theory. That's in a paper by Bourdon and Clark, I think. And they have explicit constants even. And all the kind of mixed Shimura stuff is a very general version of class field theory.
What is the version?
The mixed Shimura variety approach is a sort of very general version of class field theory. And that's where I think that's how it comes in. I'm not sure.